My guest today is Professor Rob Jackson, who's Professor of Environmental Sciences and a Senior Fellow at the Woods Institute for the Environment at Stanford University. His lab examines the many ways people affect the Earth. Welcome, Rob.
Hi, Gill. Thanks for having me.
Yeah, thanks for doing this. So, this subject that I have thought about a lot, but I don't know anything really about it. And so I want to go to one of your papers, and then I want to go to your very recent book that just came out. But in your paper here, Human Activities, this is also a very recent paper, last couple of months. Human activities now fuel 2/3 of global methane emissions. So we'll talk about methane a fair bit, I would imagine. But so you say here global average surface temperatures shattered all-time records in 2023 at 1.45 plus or minus 0.12 degrees Celsius above pre-industrial levels. Worsened by climate change-induced drought, Canadian wildfires burned 18.5 million hectares, nearly 3 times more land area than in previous year on record. And parts of the Amazon River reached the lowest levels in 120 years of data keeping, and in places recorded surface water temperatures near 40 degrees Celsius. The world has reached the threshold of 1.5 degrees Celsius, only beginning to experience the full consequences. Yeah. So I want to get some sort of macro statistics understood, Rob. I don't know a lot about this. So we got about 8 billion people around the world. And I would imagine a large percentage of them, a very high percentage of them, have been worried about this, except perhaps 100,000 politicians who have invested into companies who want to kill the world, and it's just a different story. But then about 3 billion of them, making less than $1 a day, don't have the time to think about this. But it seems like, I mean, I have to tell you this, I've been a lot of on the boundary that, when you look at long cycle temperature elevations, long cycle effects on a closed system, it's sometimes difficult to see the tactical changes. But I think we have put that doubt to that doubt is not relevant anymore, right? So I think we have conclusively proven we are on a path to some sort of destruction, so to speak. So let's start there. So what does this data tell us?
Well, the data, as you just mentioned, are crystal clear that the Earth is warming and warming faster than we expected it to. 2023 was the hottest year on record by far until this year, 2024, which is the first year for which we're over a global average of 1.5 C or nearly 3 degrees F. Now, that's not the same as being over a long-term average for 1.5 C, but nevertheless, it's a remarkable milestone that came faster than anyone expected it to. And as a consequence, last year was hot and dry, and in places like Canada, 3 times the area burned, as you mentioned in your introduction. And here in the United States, we're paying for climate disasters now. Billion-dollar disasters happen twice as often as they did a few decades ago, turbocharged by extreme climate change. And we're paying $50 or $100 billion a year more for them than we used to, adjusted for inflation. So this isn't some distant thing for our grandkids. This is change that's happening today, and it's affecting people all over the world, and especially people in poorer countries the most.
Yeah, so that's a good way to look at this. So we could sort of trace back economic cost of climate changes or climate differences. I live here on the East Coast in Connecticut by the water. I grew up by the water in South India, and we know that at least the expectations are that things are going to change quite dramatically for these places, right?
Yes, and the kinds of changes that will be most important depend on where people are, how close you are to the water for storm surge, whether you're more likely to have droughts, hail, tornadoes, hurricanes, whatever it might be. So worldwide, the weather is weird. We know that. I mean, I
Hmm.
was in my book, I talked about I was in the Amazon recently. I mean, they had a record drought. River levels there are the lowest they've been on record for at least 100 years.
Hmm.
So people are suffering. They can't travel. The dolphins are dying because the water's too hot and there's no oxygen in the water. Um,
Hmm.
it's uh, it's remarkable, and it's happening all over the world, even in the most remote parts, the tropics, the Arctic, the Antarctic. It's the places that we think about influencing the least are being strongly affected by climate change.
Yeah. So I didn't have a good appreciation of this before I read your book. And so let's go into the book. So it's called, sorry, what is it called?
It's called Into the Clear Blue Sky.
Into the Clear Blue Skies. Okay. Um, so when we think about emissions, there are a lot of greenhouse gas emissions, and they're not all equivalent. Some of them have very, very long half-life,
Mhm.
if that's the right term to use. Some of
Yep.
them very short half-life. Um, and so suppose we believe that temperatures are rising because of greenhouse gas effects. How should we think about it? I mean, what are the things that we should measure? I know, generally from a broad perspective, CO2 and methane are problematic things, but there are more to that than that, right?
There are, and we care most about carbon dioxide and methane because they're the two gases that are warming the earth the most now. Carbon dioxide gas is public enemy number one when it comes to climate change. We
Hmm.
have emitted, trillions of tons of pollution. There's an extra trillion tons of carbon dioxide floating around the air,
Hmm.
warming the earth. Most of that trillion tons will still be there in thousands of years. So it's
Hmm.
very much a long-term problem. Methane's responsible for about two-thirds as much warming as carbon dioxide over a relatively shorter time scale of decades instead of centuries. And methane is super potent, 80 or 90 times stronger than carbon dioxide over the first
Wow.
20 years.
Yeah.
But it's also, as you mentioned, it's shorter lived than CO2. It only lasts about a dozen years on average in the air. And
Uh,
that combination of potency and relatively short lifetime makes it the only greenhouse gas for which climate action today, reducing emissions, will slow the
hmm.
rate of temperature increases in climate change over the next decade or two within the lifetime of anyone listening to this show. So that's why it's become a prominent part of my research and why it's finally getting its moment in the sun, if you will, in terms of global methane agreements. People understand that it's the greatest opportunity over the next decade or two.
Yeah, I mean, I didn't have a good appreciation for this. So CO2, once it's there, it's going to be there for a long, long time. But the effect of CO2 is, let's say, 1x, and methane is just approximately 100x effect. Um, and methane lasts only for 10 years, let's say.
Mhm.
So if I were to solve this problem tactically, I should really be focusing on methane, right? I mean, we could potentially put the Earth on a happier trajectory, so to speak,
We could.
by yeah, go ahead, yeah,
Yeah, well, I mean, you're absolutely right. We need both, of course.
yeah,
We need to stop emitting carbon dioxide into the air. About half of all the carbon dioxide emissions leaves the atmosphere quickly, goes into the oceans, acidifying the oceans. It's taken up by plants. Carbon dioxide is a food for plants. But the other half, that trillion tons floating around up there, is a long-term problem. As I mentioned, they will last thousands of years. So if you had a magic wand and you could end carbon dioxide emissions today, the CO2 warming would continue for millennia. If you had a magic wand
mm,
to end methane emissions today, methane would return to pre-industrial levels of health. We could restore the atmosphere for methane within, a couple of decades. And by
mm,
doing so, we would save half a degree C of warming. And there's no other another greenhouse gas that provides such a powerful lever to slow climate change today.
So that's a very important policy directive, right? So um, you have a chapter in your book, in the first part of your book, Emissions First, Planet of the Cows.
Mhm.
Um, I grew up in India and I know all about cows. Um, so so we got about 8 billion people. I don't know how many cows there are, about a billion cows,
Yeah, a billion and a half.
billion and a half. And probably half of them are in India. I don't know. Do you have a distribution of the cows around the world?
I
In
don't have
some,
a precise country by country distribution. It isn't half of them in India. There are a lot here in the United States. There are a lot in Mexico, a lot in Brazil, quite a few in India, um, and elsewhere. So there are, certainly major countries, major producing countries that we track for cattle emissions, and cows and beef and dairy consumption contribute to deforestation in the tropics.
mm,
Estimates are that 80% of deforestation occurring in the tropics today occurs driven by the need for land for grazing cattle. So they're a major driver of forest loss today.
mm,
Cows also burp more methane or as much methane as all the oil and gas wells in the world.
mm,
So they're one of the largest sources and the largest anthropogenic source of methane to the atmosphere that we have. So we
mm,
can, to reduce emissions from cattle, we can reduce the number of cows on Earth, and we can try and reduce the emissions per cow through feed additives and vaccines and other things. And those technologies I cover a bit in the book.
yeah.
I interviewed Pat Brown, who was the CEO of Impossible Foods, and plant-based foods and reducing beef and dairy consumption is one way to slow deforestation and methane emissions. And then, however many hundreds of millions or a billion cows are left after that, we need to reduce their emissions cow by cow. That's not easy, but there are good people and companies looking for ways to do that.
Yeah, I was really surprised by this, Rob. So the burps of cows is really where the methane is coming out from. And you talk about some technologies that, sort of food additives and maybe change the diet of the cow that could potentially reduce it. Is that possible?
It is possible. It's literally quite possible. We have food additives. There are species of kelp, of algae that contain bromine and different compounds, and very, very small amounts, like less than 0.5% or 0.25% of their food by weight, added to the cow's diet can cut emissions 50% or even 80 or 90% in
Wow.
some cases, and sometimes lead to a little bit more beef or dairy production because the methane that's burped into the air is energy that the cows lose.
Hmm.
So we know that this works. The challenge is that it's hard to feed most cows on a daily basis. If they're
Hmm.
in a dairy, that's one thing. If they're in a feedlot, it's feasible. But if they're on a ranch in, Vermont or Wyoming or
Yeah.
in Brazil, we don't feed cows on a daily basis. So we have to access the cows. And that's why people are looking for
Hmm.
longer acting solutions like vaccines, things that last weeks to years rather than something that has to be fed daily. But we've got to do something to address cattle emissions.
Yeah, I thought about this. I was thinking as we were talking, maybe you can genetically alter the grass that the cows, the free range cows eat, and that reduces reduces methane. I'm just
Well,
yeah.
yeah, it's funny that you say that. I don't know if people trying to genetically modify grasses and plants to reduce methane emissions, but there are teams and companies trying to modify the microbes. That
Hmm.
there are a limited species list of organisms that generate methane. They generate methane in low oxygen, waterlogged environments. So that
Yeah.
happens in a wetland, that happens in a rice paddy, and a cow's stomach, the rumen is like a walking wetland. It's warm, it's moist, and it's low oxygen. So the
Hmm.
microbes thrive in these environments and they emit methane to the air.
Hmm.
But there are companies trying trying to change the microbes, make it less habitable for the ones that emit methane. And so there's some good work happening in this space too.
Yeah, that's beautiful. So methane is like CH4, is
Hmm.
that okay?
That's right.
And so why is the output of this bacterial action is fundamentally CH4? I mean, is there some physics we can apply to this this problem?
Yeah, there's a chain of gases that are produced. Methane is produced in part because hydrogen gets generated inside the cow's stomach, and this is a
Hmm.
way of getting rid of some of that hydrogen. Hydrogen is very reactive and in its breakdown products. So yeah, there's chemistry that we can apply, and I'm sure physics too. I'm not a physicist, but yeah, there's the thing. What's interesting about this to me is that there hasn't been a lot of work historically in this field because no one has really cared about it as much, and there hasn't been a price. You don't pay for cow burps if you're a dairy farmer. You don't really pay for methane emissions in almost any cases right now, which is a whole different discussion and problem. But now that there are incentives to cut these emissions, people and startups and companies are producing products
Hmm.
um, that cut emissions. The first commercial product was just approved in the United States within the past year, and it's a chemical. Uh, it's a product called Bovaer,
Yeah.
abbreviation 3NOP, 3NOP is the term. And that can already be bought here in the US to reduce emissions. It can be bought in Brazil
Hmm.
and New Zealand and other countries. So these products are starting to hit the market. They're not perfect, but they're better than nothing at all.
Yeah, so CH4, there are four hydrogen atoms there. I'm thinking, and you talk about hydrogen in your book quite a bit, and hydrogen has gotten some take, so to speak. I'm
Yeah.
not convinced if it's going to work. Um, so CH4, it's a lot of hydrogen there. So can we split methane into carbon and hydrogen using some sort of low energy thing?
Great question. And the low energy thing is the key part of this,
Yes.
right? So literally, yes, of course you can split the carbon and hydrogens in methane. A flare does this. The simplest way is to burn the methane. That's what a flare does, what you see
Mm.
in an oil and gas field or a refinery, rather than just let that methane go to the air. Companies aren't allowed to do that, and so they flare the gas, turn it into carbon dioxide, because
Oh,
that's the
wow.
fate of all methane released into the atmosphere. So you can do that, but it's very hard to crack open methane at low energy and low temperature conditions. This is why it's a hard gas to mitigate. So you can use catalysts, you can use microbes, you can use thermal properties, light, UV radiation, and there are, again, many people looking at lower cost and lower temperature methods of
Mm.
cracking that methane open, oxidizing it to destroy it. But it's thermodynamically difficult, 2 molecules for every million molecules in the atmosphere. So it's a
Yeah.
needle in a haystack problem. And it's a symmetrical molecule. It's not very soluble in water. It's
Mm.
hard to latch onto and hard to split open, except at high temperatures. So the best
Okay.
thing we can do is keep it out of the atmosphere to start with.
Yes, I'm fond of saying God has a sense of humor. You can see it, but you cannot solve it.
Mhm.
uh, so, if I understand this correctly, to split CH4 into hydrogen and carbon, the energy needed to do that is makes the problem worse in some ways, right?
Literally not quite right. Of course, when you burn methane, methane is natural gas, 90% of what we call natural gas. You generate energy. So it's really an activation energy problem. It takes a lot of
Mm.
energy to crack the molecule open. And then once you do that, you can extract the energy from it. But
Yeah.
it's a very steep curve to activate it. As I mentioned, it's symmetrical. It's a pointy triangle.
Mm.
It's not polar. It doesn't dissolve very well in most liquids. It's just very hard to grab onto and split open. And so it takes energy to do that. But once you split it open, you get extra energy out of it.
Mm.
But it's hard to If you think about isolating it in air, it's hard to heat the bulk air just to get the methane hot enough to break open the molecules. You have to heat a
Mhm.
bunch of other molecules that you don't need to, and you're wasting energy to do. So
Yeah.
people are, including some work in my lab, we're looking for catalysts that
Yeah.
can target methane more specifically, photocatalysts. There are microbes that consume
Mm.
methane for energy, and there are people trying to grow those microbes, maybe engineer them to be faster and better at it. So there are things that we can do to mimic nature's ways of destroying methane,
Mm.
and that's what's happening today.
Yeah. So you have a chapter in here in your book, Stop the Steal, you say.
Mhm.
Um, I was a structural engineer. My dad is a professor of civil engineering. I love steel. I loved making buildings with
Mhm.
steel. But steel is a very energy consumptive um, product, right? So so yeah, talk a little bit about that. Yeah.
Yeah, steel production contributes approximately 10% of global greenhouse gas or carbon dioxide emissions to the atmosphere. Very, very intensive industry. So imagine industries with furnaces. So think of steel, aluminum smelting, cement production, things that you have to heat material up to thousands of degrees. It takes a
Mm.
lot of energy to do that. And the best way historically for doing that has been to burn coal. And in traditional steel production, it's the same today as it was for the most part for 150 years ago. The coal provides the heat that melts the iron ore, and then it strips uh, carbon and impurities out of it. And the coal um, also provides structure in there. So you need to replace coal to make green steel that doesn't emit carbon dioxide. Very hard to do. I
Mm.
chronicle a company in my book that's the first in the world to do this, SSAB. They're in Sweden.
Yeah.
They're in Scandinavia in part because Scandinavia has had a carbon price on greenhouse gas pollution for decades. Sweden and Finland were the first nations on Earth to have a carbon price where the polluter pays. But it's an amazing process because they're generating hydrogen on site using clean hydropower. So they get clean electricity, they make the hydrogen on site, they use it on site and burn it. They replace all the coal in that process with hydrogen, and they're
Mm.
they're making the world's first green steel, and
Mm.
they're selling it to companies like Volvo and vehicle manufacturers, and they're transforming the way we're making steel and hoping to transport that steel literally in that production process around the world.
Mm.
It was a very inspiring story
Yeah.
for me to see what they were doing. I was there in person. I interviewed the CEO in the book, and it's just a beautiful story.
Yeah. Those Scandinavians, you know, they 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 tend to solve problems for the world, but they're small populations.
Hmm.
And so the question is, can they scale this? Well, I mean, there are two questions. Can we spread the policy to the 8 billion? I think scaling is a technological problem that we can solve
Hmm.
if there's will to it. But um, spreading the idea to a
Yeah,
larger population has been difficult, right?
absolutely right. And um, spreading a technology and idea is difficult for a couple of reasons. If you think about steel operations or vehicles, or ships or things, infrastructure lasts for decades,
Mm.
and companies and people don't like to throw things away that are not at the end of their lifetime. So no one wants to throw away a car that's still useful to buy a cleaner vehicle. You want to when you replace that vehicle the next time, it's smart to choose a cleaner technology then. Same thing's true for steel plants, right? So this company, SSAB, it will take 2 decades or so to replace all of their steel production with this new cleaner technology because they
Mm.
can't afford to just rip out every steel plant they have in the world and put
Mm.
a new technology in. It's too expensive. So it takes time, as the CEO discusses in my book. And frankly, it takes policies or incentives to do so. If there's no cost to emit carbon dioxide pollution to the air in the United States, and in most places, most states right now, there isn't, then most companies aren't willing to pay a little bit extra to clean up their steel production if they don't have to. They're competing against other companies who may not be paying that fee too. So it takes policy, it takes some kind of price on pollution. And
Yeah.
then just one more quick thing you mentioned. I don't think the policy needs to be the same in every country,
Hmm.
right? So you mentioned India. There are a billion plus people in India. A person there releases a tenth or one-eighth of the pollution that a person like me in the United States releases. And you have 100 million people or more in India who don't have electricity yet. So
Yeah.
India may need to build a few new coal plants to supply clean or reliable energy to people there so kids can, read at night and have electricity. So I don't think the rules for India need to be the same as the rules for Europe and the United States necessarily.
Yes, let me challenge that, Rob. And I haven't really thought about this. So we have 200 countries, and not suppose, we have 200 segmented policies. But
Mhm.
the environment is a singular thing. It doesn't matter where the pollution is coming from, whether it's coming from Oregon or New York or New Delhi or Shanghai. Pollution is pollution. Um, and so, from a policy perspective, I would argue there has to be some sort of global intervention.
Mhm.
You cannot let countries do whatever they want because they're poor. I mean, you could do that. I mean, that's what we are doing now. But that I don't think that's an optimum policy. How do you react to that?
Well, I agree with you to a point, but I think are we willing to pay uh, countries like the Indias of the world any money so that they leapfrog dirtier fossil technologies and go right to cleaner technologies? India is not just building new coal plants; they're building solar power at sort of record paces. So if we want poor nations to skip the dirty fossil fuel stage,
Hmm.
maybe we should be willing to pay them something to help them do that. And this was supposed to be the climate COP, the recent climate meeting, and that has been a very difficult thing to implement. There have been lots of pledges for climate finance and very few actual payments.
Yeah.
I think a lot more now about the benefits of clean energy for our health instead of just for climate. And Delhi's a good example. You mentioned Delhi a minute ago. I mean, Delhi has this incredible air
Hmm.
pollution now that's driven
Yeah.
primarily by, as I understand it, by burning croplands for pests and things, but it's also burning landfills and vehicles.
Yeah.
And cleaner vehicles, clean electricity emits no NOx pollution, no particulates into the air. So clean energy saves lives today. That's true in the US, where 100,000 people a year die still from coal and car pollution. And 1 in 5 people worldwide, 10 million people a year, are dying from fossil fuel pollution. That's totally
Hmm.
unnecessary today. So I like to stress the health effects now for all of us for clean energy. It's not just about climate change.
It's a health effects. Yeah. So you talk about that a lot in your book, and something I didn't really appreciate. So you look at some of the diseases like asthma and other things. Um, we tend to look at, sort of it's a temperature rising, it's a sea level rising thing, which is very easily measurable at macro. But underneath that, there's a whole suite of stuff that's happening to people, right? Because of climate change.
Because of climate change, yes. I mentioned the weather disasters before, but to go back to because of burning fossil fuels,
Yeah.
right? The ozone pollution, the smog, the NOx pollution, the catalytic converters on our cars, that gasoline-powered cars that reduce pollution. And
NOx
it's
is nitrous oxide.
NOx is nitrogen dioxide,
Nitrogen.
NO2, and nitric oxide, NO, and that's different from the greenhouse gas nitrous oxide, which is N2O. But NOx gas is the pollutant that triggers asthma and pulmonary disease, forms high temperature at thousands of degrees when you heat air, and
Hmm.
then the nitrogen, the N2, and the O2 in the air combine to form these NOx
Oh,
gases.
wow.
They
Okay.
do that in fossil fuels. It happens in lightning. It happens in the stoves in our homes, the gas stoves. And you would never stand over the tailpipe of a car just breathing in that pollution willingly. And yet we stand over gas stoves breathing the same pollutants day after day, meal after meal in our homes. And again, I promote through our own research, and I've done this personally, getting rid of gas stoves in our homes because electricity is cleaner, no NOx, no benzene, no carbon monoxide that our kids breathe,
Yeah.
and the elderly and children are the most vulnerable.
Yeah, so I'm smiling, Rob, because my daughter loves to cook on gas
Hmm.
because she says she's a OBGYN and case Western. She says, this is I have much higher control over the temperature of what I want to put on the food. So is my wife. Our home is completely electrified. We have no gas thing anyway.
Hmm. Yeah, same.
Uh, and so Yeah, so there's sort of a tactical utility that people use to make those decisions, but what they're not aware of is sort of the strategic disutility for society, right? So this is part of your book. And so how do we solve this problem? I mean, how do we educate a larger population how this thing works and how it affects society?
Yeah, fantastic question. I do a lot of work developing new methods, instruments for measuring pollution that we can't see or haven't been able to see before. With my friend Nathan Phillips, a different chapter in the book, we mapped thousands of gas leaks across cities like
Oh yeah,
Boston
you want to
and
talk about that? Yeah.
yeah, we can talk about that. But pictures, when you see a picture of every street in Boston with thousands of leaks coming out of it, it motivates people to change. And it isn't just
Mm.
about climate change in that case, it's safety. So similarly, we're developing new methods to measure, to quantify the pollution that forms indoors in our homes when we burn gas in our appliances. And we've shown that NOx and benzene builds up not just in the kitchen where the cook is, but in bedrooms down the hall, and rises above thresholds with hoods on and off in
Yeah.
many cases, and it stays above health thresholds for hours at a time.
Mm.
So when you wouldn't want to breathe this air outside, and we don't want to breathe it inside day after day either. But we don't think about the pollution that we're breathing inside because we can't see it.
Yeah.
And so I think it's important for us to quantify that pollution, make it easier for people to see, figuratively speaking.
I haven't really thought about this, Rob. So could we have some sort of pollution measuring device inside the home
Well, we
someday?
could, and of course we do for things like carbon monoxide. We already
Yeah.
have sensors for smoke and CO. There isn't a low-cost sensor for NOx gases, and there's no low-cost sensor at all for benzene. We
Yeah.
actually have a grant to try and develop some of these sensors, and what we need are sensors that cost, $100 instead of hundred
Mm.
thousand dollars, like some of my instruments I use in the lab. So we need much cheaper sensors. Then we can put them in thousands of people's homes and look at what happens when you turn the burner on your gas stove or turn the oven on, and watch how fast the pollutants rise in the air. We need a lot more data and information to assess risk for
Yeah.
people.
So talk a little bit about, I know that you did some work in Baltimore, Washington area, and then in Boston. Um, and I had no clue about this. So methane leaks from old pipes, right? That's what you're finding?
Yeah, we did. It's funny you bring that up because I was at a workshop last week in Washington, D.C., the American Geophysical Union. And as I was walking around the streets of the city, I was still smelling gas leaks. And once you sort of notice this, you get sort of attuned to it. So with my friend and colleague Nathan Phillips in Boston, we put new methane lasers into cars and paired them with GPS units and literally drove every block of cities like Boston and DC, Manhattan, mapped thousands of leaks in these cities. And in Boston and Washington, D.C., within a year of publishing our data, the utilities and the states passed laws and rules to accelerate pipeline repair and replacement.
Yeah.
So people visualizing these thousands of leaks, every one of them an explosion risk,
Mm.
motivated people in the legislature and at the utilities to do something about the problem. And so that's the power of visualization. If we can make pollution more apparent to people, they're more likely to act on it. So nobody had
Mm.
done this before, and we were able to get a lot done with the information.
Yeah, I mean, the work that you're doing is really, really important. What I'm
Thanks.
struggling with is, can we get this into the psyche of policymakers somehow? Um, and I'm becoming more and more pessimistic, Rob,
Hmm.
about the world. I mean, we have a lot of data now. We know scientifically why something is wrong and something might be a way to solve it. But we cannot get this into policy yet, right? So are we are we just trying to understand things and then we don't actually make a difference to the population?
I don't think that's it at all. I think there are several factors at play. There are, billion dollar, trillion dollar industries that don't want to change and fighting that change in some cases with disinformation. There's inertia. I already mentioned that it takes decades to change infrastructure, so it takes time. And there are practical factors like energy costs and different costs of electricity versus gas around the world and in
Hmm.
different parts of the United States. So all of these factors affect how likely we are to change. But I look back at a time. I like to talk about environmental successes in class.
Yeah.
We have lives saved by phasing out leaded gasoline, by the Montreal Protocol that was signed by Ronald Reagan, a Republican president, the Clean Air Act, my favorite, that saves 100,000 or more American lives every
Hmm.
year at a 30-fold return on investment, $30 saved for every dollar spent to reduce pollution. Worker productivity is improved, our health's improved. All of these bills were bipartisan historically,
Yeah.
with Republican and Democratic support. And we've kind of lost that. I regret that maybe more
Yes.
deeply than anything else over my lifetime. And no political party had a monopoly on environmental action, but we're headed to a world where the environment has become a polarized issue. I don't understand that. It's
Hmm.
everyone in the world wants cleaner air and water for our kids, wants our children to be healthier, but it's become this narrative that climate action somehow is a liberal plan to control our lives instead of seeing it as an opportunity to
Yeah.
breathe cleaner air and drink cleaner water, which is what clean energy provides for us today. So I regret that more than
Hmm.
anything else, the polarization of environmental action.
Yeah, I mean, it's a bit of a steep climb in the sense that when science loses, you have a different society. And I argue that that's the society that we are in, where science is not that important anymore. Um, and so it's very, very difficult to affect policy from that angle, right? Because so when people start to believe science is a conspiracy theory, um, there's really no way to get around it because scientists are not going to be able to do that because they're basically going to show you data, they're going to show you hypothesis, and they're going to say at a 95% level, I believe this is true. And then if most of the public is saying, well, how about the other 5%? That
Mhm.
means that you don't know, right? So there's a conceptual difficulty here. And I think science is losing in the US and in a lot of the other parts of the world as well.
I agree. We seem to be in a phase where we want to be destroying institutions. That's an opinion of mine. That's not a scientific conclusion. But we're tearing the courts down. We're tearing the FBI. We're tearing its science and health. Um, we have as an example, we have thousands of years of experience of the world without vaccines, right? We know what happened in the past when there weren't vaccines, and we do not want to go back to that place. That's not a climate change issue, but it's a public health issue. So we seem to be almost willfully trying to destroy the institutions that have helped us build this country. And I think in the scientific community, we do have something unique to say. We need to say it with humility. We don't know everything. And sometimes just because you're a scientist doesn't mean that what you think is the right thing to do has to happen, right? So I can give you data about air quality and climate. That doesn't mean a person has to reach the same conclusion about acting on those data that I would reach.
Hmm.
And that's a societal issue and a behavioral issue. But yeah, I deeply regret a period of time that we seem to be entering where we're all of a sudden we don't want information from so-called experts because they have a have an agenda. Frankly, I mean, I trust health professionals. I trust people who study the earth for a living more than I trust some person who blogs on the internet. So, science is an institution. We've built this country on science and technology and morals and other things too. And I just deeply regret the loss of some of those in recent years.
Yeah, so sometimes I feel, Rob, I mean, this is not in your research, but I just want to get your perspective on this. Sometimes I feel that the the problem with science is that we're not going to be absolutely sure about anything because there isn't enough data to have a probability of 1.0 on anything, right? So even climate change, even all the stuff that we talked about, there is no event with a probability of 1.0. And so scientists go out there and say, we are reasonably sure this is the case. And most of the people say, yeah, this guy doesn't know what the heck is
Yeah,
going
that's
on.
true.
Yeah, yeah.
Yeah, I think the hardest word to convey to the public that we use regularly in the scientific community is uncertainty. And uncertainty doesn't mean we don't know or don't know anything. It means there might be a 95, a one. We often use a 95% probability level as a convention. It means a 1 in 20 chance of being wrong. It might be 99%, one in 100. But it's sure not, it's a lot better than 50-50. That's all I'd say,
Yes.
or 60-40. So when we talk about uncertainty in the scientific community, we're acknowledging that we never have perfect information. We will never be able to say something with complete confidence. There may be an apple that drops off the tree tomorrow that doesn't fall to the earth. And there's no way to say that that's impossible. It's just after enough apples fall and after enough rockets launch, you gain confidence in what will happen. And yeah, uncertainty is hard to convey to the public. Climate change has some uncertainty. We don't know exactly what the bounds of sea level rise will be. We know that the sea has already risen because of melting ice and thermal expansion of water. As you heat water, it expands in volume. So that's a fact. That's not an observation. We don't know exactly what the future sea level rise will be because it depends on how much the Earth warms and how much snow falls and a whole bunch of factors. We can't answer all of those with perfect certainty, but we can know a lot about something and still talk about its uncertainty, but that uncertainty gets used against us. Like we'll see, they don't really
Yeah.
know. And uncertainty is a convention for us. It's a way of acknowledging the sources of error in the data that we have and use. And it's an important part of what we do as scientists.
Yeah, so I want to ask you this. So we'll complete with this. So in another podcast, I argued the the first course that a primary school kid should have is statistics and hypothesis testing. Because there is no reason to teach kids Newtonian mechanics anymore because we can program computers to do all that stuff. I mean, you don't need humans anymore for that. It's deterministic. It's a deterministic theory. Um, but we have to teach kids, I believe, to take data and come to a conclusion that is typically going to be uncertain. And so, it's a question of how do you create a hypothesis? How do you test it? How do you get comfortable with the conclusion? That skill is what kids need. I mean, it's not Newtonian mechanics that they need to study, I think.
Yeah, it's a great point. I think to teach statistics, you have to know something about math. probability distributions. So, maybe that's a class you could teach elementary schools students, but it is clear that research shows us we're very bad at assessing risk,
Yeah.
particularly long-term risk, and risk is essentially a statistical concept. The insurance companies, they've come out and said publicly that they think climate change is real. They think climate action costs less than the
Mm.
disasters and damage that will come from climate change. So companies like Swiss Re are telling us we need to act and spend billions of dollars to stave off climate change, or we'll spend more money over the next few decades. So they understand risk. They study risk for a living. But
Yeah.
we, as people, really don't know how to think about long-term risks over decadal timescales. It doesn't come easily for us as people. So I have a master's
Mhm.
degree in statistics. I'm all for stats, knowledge, and learning. I might want my kid to study art or something else in kindergarten too, but that's a different issue.
Yeah, I love art. That's probably a good way to live. So excellent, Rob. So the book is Into the Clear Blue Sky. I really enjoyed reading it. I learned a bunch of stuff from it, which I had no clue about.
Thank you.
Um, and I hope we keep pushing. We keep pushing humanity forward. We have had some setbacks from a political perspective in many countries, and I hope we can get over it and then continue on a better journey.
Yeah, thank you, Gil. Thank you for caring. Thank you for helping me spread the word about my book. The website is intotheclear.com. Just today, it was named the best science book of the year by Scientific American.
Yeah, that's
So I'm
fantastic.
grateful for that. And yeah, I wrote this book in search of solutions and hope and optimism. And the book, I think of it as a how-to guide to restore our air on a journey from climate despair to climate repair. So it's hopeful. I interview people around the world who are making a difference individually,
Yeah.
in their neighborhoods, CEOs of companies, institutions. So it was a quest for me to find hope in the world, and I came away more hopeful than before I started it, and I hope
Mm,
that readers will too. So thank you
mm.
for having me, and best of luck with your podcast.
Thank you. Excellent. Yeah, thanks for spending time with me, Rob.
All right, take care. Bye bye.